This nuclear reactor has no pumps, no mechanical cooling system, no diesel generators standing by to keep the core from overheating. Nothing that requires electricity to function. And if you cut all grid power, remove every operator from the control room, and eliminate every source of external water, simultaneously, the core stays submerged, cooled, and stable for a minimum of 72 hours. With nothing running, with nobody there. That is not a marketing claim. That is the certified result of a safety evaluation conducted by the Nuclear Regulatory Commission of the United States. And it raises an obvious question. How? How does a nuclear reactor, the most complex, most tightly regulated energy machine ever built, keep itself cool with no mechanical systems, no power, and no human intervention? The answer is a piece of physics so elegant it almost feels like cheating. But getting to that answer required first understanding why the last generation of Western nuclear plants cost so much more than anyone expected. And then rebuilding the entire concept from scratch. That story has two layers, and both of them are happening right now, in real construction projects, on real sites, for the first time in history. Two pillars. This is the schema. Pillar 1. The architecture. How nuclear went from 50-year civil engineering disasters costing $35 billion to a product you manufacture in a factory, load onto a truck, and install. And why the economics of that shift are harder than the technology. Pillar 2. The physics. How geometry replaced pumps. Why this reactor has no mechanical cooling. Not because of better backup systems, but because of where the components are physically positioned inside the pressure vessel. And what that means for where these reactors can be built and who is paying for them. Let's build. There is a number that explains everything that went wrong with nuclear construction in the West. The number is $35 billion. That is the final cost of Vogtle Units 3 and 4 in Georgia. 2 reactors. Construction started in 2013. They finally came online in 2023 and 2024. 11 years. $35 billion, more than double the original estimate. And these were not experimental machines. They were an existing, proven design, being built in the United States by experienced contractors with full regulatory approval. What went wrong? Every single piece of that plant was built from scratch on an open construction site, in the weather, by crews that turned over constantly. Every weld was a custom weld. Every concrete pour was a custom pour. Every pipe fitting was custom designed, installed by hand, inspected on location. Engineers have a name for this approach. They call it the stick-built method. And as a business model for nuclear energy, it is catastrophic. SMR designers are attempting to reverse that completely. The key metric they use is the stick-built fraction, the percentage of construction work done on-site versus in a controlled factory environment. For Vogtle, that fraction was essentially 100%. For the BWRX-300 that GE Vernova Hitachi is now building at Darlington in Ontario, the first commercial SMR under construction in any G7 country, the design target is below 20%. The reactor pressure vessel, the steam generators, the containment structure, fabricated to nuclear-grade tolerances in an indoor factory with the quality control standards of aircraft manufacturing, then transported and installed. The goal is not just cheaper construction, it is predictable construction. Because in nuclear, cost uncertainty is what kills projects. And here is the part the industry rarely explains in public. There is a regulatory shortcut built into the modular design. A standardized reactor can achieve what regulators call type approval, certify the design once, then deploy it repeatedly without relitigating the full safety case at every new site. That eliminates one of the biggest sources of cost uncertainty in the industry. So the factory model is genuinely compelling. And then, and this is essential to understand, it failed. In November 2023, NuScale Power Corporation and its utility partner UAMPS canceled what was supposed to be the American showcase for small modular reactors, the Carbon-Free Power Project in Idaho. And I want to be precise about why, because the simple story gets it wrong. The NuScale design did not fail. It was the first small modular reactor in history to receive full design certification from the Nuclear Regulatory Commission. The technology passed every test. What failed was the economics. The projected electricity price jumped from $58 per megawatt hour to $89 per megawatt hour, a 53% increase, driven by inflation and rising interest rates. When those numbers landed, the municipal utilities that were supposed to be customers backed out. At cancellation, only 116 of the 462 planned megawatts had been subscribed. Less than a quarter. The project never broke ground. And that is exactly the problem. Factory economics only work if you have a large enough order book to justify the factory. Without enough buyers committed upfront, the per-unit cost never comes down. And without a first working unit to point at, it is very hard to get the buyers that create that scale. It is the textbook chicken and egg problem, and it sits right at the heart of the advanced nuclear industry right now. The Darlington project in Ontario is now the one that has to break that cycle. Construction license issued April 2025. Provincial authorization May 2025. Target commercial operation by the end of 2029. First commercial small modular reactor in the G7. Everything rides on this one. But the factory model only makes sense at all if you can also shrink the safety perimeter around the reactor. Smaller exclusion zones, different insurance profiles, closer siting to the industrial users that need the power. And doing that requires answering the question we started with. How do you keep a nuclear core cool with no pumps? Let me tell you about the actual worst-case scenario for a nuclear reactor. Not the version from movies, the engineering version. It is not an explosion. It is heat that you cannot remove. Even after a reactor shuts down completely, control rods fully inserted, fission essentially stopped. The fuel keeps producing heat. The radioactive decay of fission products generates roughly 7% of the reactor's operating thermal power immediately after shutdown. 7% sounds small. In a large reactor, that is still tens of megawatts of heat. And it does not stop quickly. It declines over days and weeks. Engineers call this decay heat. And managing it is the central challenge of nuclear safety engineering. The conventional approach uses machines. Electric pumps circulate coolant through the core. Diesel generators back them up if grid power fails. Operators monitor everything. It works. The global safety record of nuclear power is genuinely good. But the system requires energy and human action to function. Every component in that chain is a potential failure point. And as the world saw at Fukushima in 2011, when the tsunami knocked out both grid power and backup power simultaneously, if the pumps stop, the decay heat accumulates, and you have a crisis. The passive safety approach asks a fundamentally different question. What if cooling was not a machine? What if it was a physical law? The mechanism is natural convection. And it is one of the most elegant things in engineering. Hot fluid is less dense than cold fluid. That is not a design choice. That is thermodynamics. So if you arrange the reactor components in the right geometry, if you position the steam generators physically above the reactor core, inside the same pressure vessel, something happens automatically. Hot coolant rises from the core. It reaches the steam generators above it, transfers its heat, cools down, becomes denser, and sinks back to the core. The loop runs, continuously, without any pumps. Driven entirely by the temperature difference between the core and the steam generators. Engineers call this the delta T, the difference in temperature. And in this design, the delta T is the pump. This is not a metaphor. This is the Nuclear Regulatory Commission, certified cooling mechanism for NuScale's VOYGR reactor design. The geometry of the reactor, the fact that the steam generators are physically positioned above the core inside the same vessel, is what makes passive cooling work. Change the geometry and you lose the effect. This is why the design is integral. Everything in the same vessel, in the right order, because the order is the safety system. What does this mean in practice? NuScale tested the scenario where everything fails simultaneously. No grid power, no operators, no diesel generators, no external water supply. What happens? Decay heat drives natural convection through the core. That transfers heat to the containment vessel wall. The wall conducts heat into a surrounding pool of water. That water boils slowly and vents steam passively. The core stays submerged and stable for a minimum of 72 hours, with nothing running, with nobody there. That is the certification basis, not a theoretical claim. A tested, NRC-certified result. X-Energy takes a completely different path to the same destination. Their X100 reactor uses what are called TRISO fuel pebbles, small spheres, roughly the size of a billiard ball, each containing tiny uranium particles wrapped in successive layers of pyrolytic carbon and silicon carbide ceramic. The ceramic layers act as a pressure vessel for each individual fuel particle. Accident testing has validated the integrity of those shells at temperatures that no credible reactor accident can generate. The XE100 is physically incapable of producing the conditions needed to fail its own fuel. The safety case is not "we have better pumps." It is the fuel cannot fail under any accident scenario the reactor can create. Two very different designs. Same underlying logic. The safety argument is not about backup systems. It is about physics, and physics does not have a maintenance schedule. Now here is why this changes everything about where these reactors can be built, and who wants to build them. A reactor with a passive safety case and a compact modular design can be sited in places and at distances that a conventional large reactor cannot. Smaller exclusion zones. Different regulatory burden. The possibility of co-locating directly with the industrial user that needs the power. And that last point is why Microsoft, Meta, and Amazon are making the largest bets on nuclear energy in decades. Not because of climate policy, because their AI data centers need power that is flat, continuous, and absolutely reliable at hundreds of megawatts per campus. And the load profile of a hyperscale data center is almost perfectly matched to the operating characteristics of a small modular reactor. That is not a coincidence. That is an infrastructure procurement decision. So this is where nuclear energy stands in early 2026. The physics of passive safety has been tested and certified. Thermodynamics does not negotiate. The factory manufacturing model is theoretically sound and is now being tested in the real world for the first time at Darlington in Ontario. The demand signal from the technology industry is the clearest commercial pull the advanced nuclear sector has ever had. But the factory model has already failed once, at Idaho, because the order book was not there to support the economics. And Darlington is carrying the weight of that lesson. It has to prove that a first-of-a-kind SMR can be built on schedule and within budget. It has to be the reference unit, the proof that the assembly line is worth building. And there is a second challenge that this video has not touched yet. Even if the physics works and the factory works, these reactors need a fuel that barely exists in the Western world right now. That is the subject of the next video. The schema is drawn. The variables are live. Subscribe to @Project Schema. The next system is already on the board.